Okay, so we've got this great set of sources you sent over, all about lasers.
Yeah, it's a fascinating topic.
It really is. They feel so futuristic sometimes, but
Yeah.
they're just part of everyday life now.
Absolutely everywhere.
So our plan today is, well, to unpack the main ideas from these sources, really get into the quantum mechanics, how they actually work,
Right, the physics behind it.
and then look at all the incredible uses that have sprung up. It's kind of amazing how it connects, fundamental physics,
Yeah.
even Einstein's early ideas,
Mm-hmm. Stimulated emission.
to the tech you use without even thinking about it.
It's a great example of that journey from theory to application. That idea, stimulated emission, was proposed way back early 20th century.
Right.
But the first working laser wasn't until 1960. And since then, well, it's just transformed field after field.
And the key thing, as the sources point out, is that a laser isn't just a stronger light bulb. It's fundamentally a quantum device.
Exactly. It's special properties that really narrow directional beam the pure single color or wavelength. That all comes directly from how atoms behave at the quantum level.
Which brings us to energy levels, right? Quantum mechanics 101, sort of. Atoms can only exist in specific energy states.
Like steps on a ladder, yeah. They absorb or emit energy in these fixed amounts, these discrete chunks called quanta.
And the sources mentioned some early attempts, like the maser used just 2 energy levels,
Yeah.
but that wasn't quite enough for a really practical laser.
Well, it works, but you need something more sophisticated for the kind of lasers we rely on now.
Mm-hmm.
The core process is stimulated emission.
Okay.
So you pump energy into the atom's light or electricity, usually pushing their electrons into a higher energy state, an excited state.
Right.
Now, normally, they just fall back down whenever, randomly, spitting out a photon. That's spontaneous emission. But the trick is,
You hit them with another photon.
exactly, a photon with precisely the right energy. That incoming photon stimulates the excited atom to drop down. And when it does, it releases its extra energy as another photon that's a perfect clone of the first one. Same direction, same wavelength, same phase. They're coherent.
Okay, so that's how you get the beam. But the sources really emphasized a problem, especially with what they called the 3-level laser design.
Yes, the big challenge is achieving and maintaining population inversion.
Population inversion. Okay, what's that?
It's an unnatural state, really. You need more atoms sitting in the higher excited energy state than in the lower state they're going to drop to. That's essential for stimulated emission to dominate over absorption.
Because otherwise the incoming photons just get absorbed by the atoms in the lower state.
Precisely. Now, in a simple 3-level system, the lower state for the laser transition is often the ground state, the lowest possible energy level.
Okay.
Atoms drop there after emitting their photon, and that ground state fills up very quickly.
Yep.
It becomes really hard, almost impossible for continuous operation to keep more atoms up high than down low.
Right, because everything wants to end up at the bottom.
Exactly. It's fighting against equilibrium.
And this is where the sources highlight this really clever bit of engineering, the 4-level laser.
Yes, that was the breakthrough. It cleverly bypasses the ground state problem.
How does it do that? It adds another level.
It adds 2 levels, strategically placed. You pump atoms way up high. They quickly drop to a special intermediate state. It's called a metastable state.
Metastable, meaning
Right.
sort of stable but not completely.
Right. Electrons tend to hang out there for a relatively long time, microseconds or even milliseconds, which is ages in atomic terms. This allows a large population to build up in this metastable state.
Okay, so you get your population inversion starting from that metastable level.
Exactly. Now, stimulated emission happens, and the atoms drop down, but not to the ground state. They drop to another intermediate level, one that's still above the ground state.
Oh, I see.
And this lower laser level is designed so that atoms leave it very, very quickly, dropping the rest of the way to the ground state almost immediately.
So that lower level stays relatively empty.
Precisely. It empties out fast. So you easily maintain more atoms in the long-lived metastable state above it than in this rapidly emptying intermediate state below it.
You've got your population inversion between those 2 intermediate levels.
You got it. And that allows for continuous laser operation, not just short pulses. That 4-level design is fundamental to most modern lasers.
The sources mention pumping this energy in with electricity or light, and that tiny semiconductor lasers, diode lasers, are super common now.
Yeah, they're in everything from barcode scanners and pointers to the fiber optic cables carrying, well, this conversation probably.
Okay, so we have this incredibly specific, intense, controllable light thanks to quantum mechanics and clever engineering. What can you actually do with it?
The applications. The sources cover a lot. Think information first. because you can focus the beam so tightly and switch it incredibly fast.
Billions of times a second.
It's perfect for reading data, like on old CDs or in scanners, and crucially for sending data down optical fibers for the internet and telecommunications.
That tight focus also means high power density, right? Even if the total power isn't huge.
Exactly. You concentrate the energy in a tiny spot. That intensity is what lets lasers cut, weld, or vaporize materials in industry with amazing precision.
Way more precise than a mechanical tool sometimes.
Oh, absolutely. And that same precision translates to medicine.
Right, laser surgery.
Delicate operations,
Yeah.
sealing blood vessels, even things like vision correction, reshaping the cornea. It's all about controlling that light energy precisely.
So it's really striking how you go from, electrons jumping between energy levels in an atom
And manipulating those jumps with stimulated emission.
and engineering this four-level system
Hmm.
to cutting steel, transmitting global information, and performing eye surgery.
It's a perfect illustration. This deep dive really shows how these fundamental quantum ideas, these discrete levels, stimulated emission, the smart engineering, lead directly to technologies that, well, define so much of our modern world.
Absolutely. It makes you wonder then, considering how lasers are so deeply tied to this weird, discrete quantum world, these specific energy steps,
Yeah.
what other completely unexpected applications might still be out there waiting for us to figure out the next quantum trick?